Okay, this screencast is going to cover mass spec. Mass spec is used to find relative masses and abundances of isotopes of elements. That's what we've seen earlier last year in the course. We can also use it to find the relative molar masses or the molecular mass of compounds. And we can do that to help identify unknown or new compounds. And also, it's used by forensic chemists to identify materials like crime scene, drugs, that kind of thing. Okay, if you remember, we looked at mass spec last year, and we talked about how it worked. It was if you remember, VIAD, right? You vaporized a sample, then you ionized it by hitting it with high energy electrons. You accelerated it using a magnetic field. It was deflected through a magnetic field. One of these might have been an electric field. And then it was detected at the end of the mass spec. We're not going to focus on how it worked like we did earlier. Now we're going to look at the graphs that you get from the mass spec and how you make sense of them and how it helps identify compounds. And I thought it would be cool just to see some of the equipment. I know this picture's a little fuzzy, but that's a mass spec, and then this is a mass spec as well, just to give you an idea of what it would look like if you were in a lab setting. So again, going over kind of how it works. Excuse me, I'm sorry. Oh, goodness. So a substance is injected into the mass spec and it's vaporized. Right? Then it is accelerated and changed into a positive ion by being bombarded by that should be an electric gun. All right, so high speed, high energy electrons hit the sample. Then it's accelerated in a directed around a curve. Heavier substances curve less than lighter substances, having to do with the momentum. The other thing that is maybe different than what we highlighted before is that with this bombardment of those high energy electrons, you do actually break the molecule apart. Last time we focused just on isotopes and atoms, but with a molecule, you with that high energy electrons, you break them into fragments. Okay, and it's these fragments that are charged that are picked up in this mass spec, and kind of by working backwards, you can determine what the different components are of a molecule. Okay. Just remembering that atomic masses are based on the carbon-12 isotope, so the mass spec is going to be set up to give relative atomic masses based on that. That's what all atomic masses really are based on. Reviewing a little further still, just looking at isotopes. Neon has 3 isotopes. And when it is put through the mass spec, the neon is hit with that high energy electron, and it forms actually positive neon isotopes. And those isotopes get deflected around a bend, and then it's detected at the end. The heavier isotope, this neon 22, if you remember, this top number is your mass number, which is the neutrons and protons. Okay, and that is okay, so this is a neon. I was talking about this being the mass number, protons plus neutrons, this being the atomic number. The peaks that you see correspond to the 3 isotopes that make up neon. The size, oh goodness me, the size of the peaks have to do with how much of that substance is relative to the other substances that are present. So you can see neon is mostly the neon 20 isotope. This was your relative abundance, Remember, to calculate an average atomic mass, you take the relative abundance, multiply it by its atomic mass for the individual isotope. You can sometimes use just the mass number. If they give you more information, then you should use that. Then it's the percent times the atomic mass of the other isotopes, and then you can get the average atomic mass of the element neon. All right, but it's important to note that these peaks show up because those neon isotopes were given a positive charge. All right, and this was the 2210. Okay, and the same thing we can see for boron because we have two peaks. We can know that boron has two isotopes, boron 11 and boron 10. There is much more boron 11. Looking at the relative sizes of these lines, the last mass spec gave you the percent abundance. Here you would have to figure it out. And if you look, this boron 11 looks like it has a relative abundance of 100, and this is of 25. I can't have 125% of a sample, so really you would take your 100 over your 125 times 100 to get your percent abundance for your boron 11. Okay, and do 25 over 125 times 100% for the boron 10. Okay. All right, so when we look at the mass spec for a molecule or a compound, we are going to form what's called a molecular ion. Right? And this is a molecule with a positive charge formed by the removal of one electron. We're going to write that as a capital M with a plus sign. That is the molecular ion. It's formed by getting bombarded with those high energy electrons. And again, because of all that energy, the molecule sometimes breaks apart and makes fragments. Those fragments will sometimes have a positive charge. If they have a positive charge, then it is going to show up as a peak. Ooh, I don't know why I did that. So if this fragment, again, has a positive charge, it is going to show up as a peak on your mass spec. And we can use the molar mass or the molecular mass of those fragments to get an idea about the structure of the compound. All right, so this fragmentation pattern gives us some useful information about the structure of the compound. Important to note, only the positive ions are detected by a mass spec because those are what's going to be deflected to the detector. Right? It does not detect neutral fragments. It's important to note that sometimes we'll see like a little peak that's at the molar the M+1 peak, it's called. And this doesn't really represent a different fragment. What it represents is the presence of this carbon-13 isotope. Okay. It only has about 1.1% abundance, so most of carbon is the carbon-12 isotope, right? But sometimes you'll see right next to your M+ peak, you'll see like a little peak, and that's your M+1 peak, and that's just due to this extra neutron in the carbon-13 isotope. All right, so let's look at a mass spec and see what it has to tell us. Okay, what you do is you look over here for the highest molecular mass. Okay, and this is our M+. This is the highest molecular mass, so that has to be the biggest piece that was detected, that has to be the entire molecule. Okay, remember that it is going to have that +1 charge. You can see just this little peak here, and that has to do with there being that carbon-13 isotope. All right, so that's the M+1 peak. This is your M peak. If you notice, there's this big peak at 45 that's just one atomic mass unit away from the largest peak, and that represents this fragment. If you notice, just a hydrogen has broken off. Please notice that there is that plus sign. All right, so that was picked up. And you'll see that there's common fragment masses that you look for, all right? And there should be a table in your notes, okay? Fragment 31 is CH3O, okay, with a plus. 29, you've got C2 CH3 plus. And then at 15, this is fairly common as well as a CH3 with a plus. All right, this is also pretty common. All right, so what we're doing is we're looking for these well-known peaks. That's peak 30, sorry, this is 29. The 31 peak. We're looking for these well-known peaks to give us an idea of, do I have some of that alkyl chain with the C2H5? Do I have methyl groups? So the idea here is, so if I have ethanol, okay, my M, there should be a peak at 45. If I take this molecule and it breaks here, I'm going to have a loss of that methyl group, but because this has the positive charge, it's going to be picked up by the mass spec and shown as a peak, and that peak will be at M over Z 31. Okay. If the molecule breaks here, I'm going to lose this hydroxyl group. This is going to have a plus charge, and it's going to show up as a peak at 29. Going to sound like a broken record, but I'm going to say it again. When fragments form, one fragment is going to have a positive charge, and that is the fragment that's going to show a peak. Okay. So the mass spec only picks up things that are positively charged. So if you're identifying things in a mass spec, you have to include that positive charge. Okay. So if we look at this octane piece, we'll do this on the screencast, and then we'll look at a couple in class. Octane, this is my M plus. Okay, and you can see a little peak here for the M plus 1. It's 114. Now, if I look from here to this 85 peak, okay, I've lost part of that chain. Remember, I have octane. Okay. If I lose, if my molecule splits here, okay, and the positive charge goes here, that's going to be this peak at 85. Why don't you tell me what peaks you think you may see at 71, 57, 43, and 29. Okay. And that finishes out this. We'll talk about this mass spec and a couple more when I see you in class.